Welcome to our Rohde & Schwarz webinar with the title Small Cell, an essential paradigm shift for cellular networks. My name is Nicola Serda. I am product manager for the CMP200 and will guide you through the webinar. First, we would like to explain what a small cell is and how it contributes to enhance the network. Then, we deep dive into technical details about functional splits and deployment scenarios. As a test and measurement company, of course, we are competence carrier for the various testing challenges, and we will share our knowledge within this webinar. At the end, we will show a quick demonstration with our one-box tester CMP200 and give you a summary. My partner for this webinar is Mahesh, who is located in Singapore and an absolute expert when it comes to networks. Mahesh, could you please explain the magic behind small cells?
Thanks, Nico. Hello all, welcome to the webinar. I am Mahesh and I'll walk through the trends around the small cell market and later the challenges and solutions around the test cycle of a small cell. So let's start with the definition of small cell. What is a small cell? Small cell is a compact base station covering smaller coverage area, serving fewer users and with smaller power. The industry also defines a small cell as everything which is not a macro and not using massive MIMO. And 3GPP defines the base station classes, and of them the three: wide area base stations, medium range base station which is a micro cell, and the low area base station which is a pico cell. And here the low area and the mid range or medium range base stations come under the small cell umbrella. Looking at the different roles the small cells have played across the different generations of technology, small cells have been there from 2G, 3G days, and then its role was to provide coverage. Yeah. And later in LTE networks, the small cells were providing not just the coverage but capacity without adding additional spectrum. And now in the 5G era, network operators use densification as an important strategy to provide seamless 5G services, not limited to coverage and capacity, but also to provide performance. Especially with the millimeter wave rollouts around the corner, the small cells are a better choice compared to macro cells given the propagation characteristics of a millimeter wave. Now looking at the opportunities. So with the availability of 3GPP release 16, the vertical industries are adopting 5G for their digital transformation journey. And here the small cells play an important role as private networks are used to cater to these different use cases. Private networks are networks custom built according to the customer needs, and here the small cells and the macro cells have to complement each other to provide a service according to the different customer use cases. Some of the use cases are smart cities, healthcare, oil and gas, stadiums, airports, smart factories, logistics, seaports. And these customers, say for example in US, the CBRS spectrum. So here we have at least like 200 players from the different verticals having licenses to operate their own private networks. And another trend to notice here, it may not be always the mobile network operator who is providing the public network to us today who will be laying out these private networks. There will be new players who will be providing such private networks, which can be from the system integrators, equipment vendors, and also neutral hosts. And the market size of a private networks is around 3.5 billion and is estimated to grow at a rate of 18% until 2026. it's a huge opportunity for the small cells. And here, the small cells are an essential strategy to realize the full potential of 5G in both indoor and outdoor environments. Next, looking at the statistics of the small cells deployment by spectrum wise, then you see currently FR1 is the dominant deployment scenario. And moving on from 2022-23 onwards, you can see the millimeter wave small cell deployment getting increased until 2026, maybe where the FR1 and FR2 deployments will be at par. And then you also have a graph here about the small cell deployments by verticals. This is a cumulative value. And if you see here, across the different verticals like utility, energy, manufacturing, retail, local government, transport, and healthcare, there is no clear winner between the FR1 and FR2. They both play an equal role when it comes to vertical industries and private networks. With that thought, let's move on to the next slide, where I want to remind you of how a small cell looks like so far. So here we have the base station unit and the radio unit with the transceiver and analog RF. In the baseband unit, you have the L1, L2 processing, synchronization, the baseband processing, which basically provides a baseband signal to the radio unit and then further to the external antennas. This is a 2T, 2R scenario. And especially if you look at the baseband interface between the baseband unit and the radio unit, it's often a proprietary interface used for communication between the MAC and the physical layer. And then going forward, here there was FAPI interface used. FAPI is a functional application programming interface for communication between the MAC and the physical layer. Then some typical specifications of small cells. Here you can see the power rating, the maximum weight of a small cell ranging from 2 kgs to 8 kgs, and then the modulation scheme in downlink, the 256 QAM, uplink 64 QAM, and then the MIMO layers in downlink and uplink going up to 8 layers, and transmit receive antenna ports going up to 8T, 8R configuration in FR1, and then in FR2 up to 32T and 32R. Yeah? And then when it comes to the antennas, the FR1, it's external, and for FR2, it's integrated. Spectrum, it can operate in licensed band, unlicensed band, and shared band. So the technology, it can be 5G standalone or a dual mode, LTE and 5G. Coming to the split options, option 6 and option 7 or both. Option 6 and option 7, this we will deal with in the next slides. And fronthaul speed 10 or 25 gigabits per second. Going forward, let's look at the open standardized interfaces. So the industry is moving towards open and standardized interfaces. So here the 3GPP studied in the technical report 38.801 the different possible functional splits between the centralized unit and the distributed unit. Objective split architecture provides scalability and also cost-effective solutions for networks, and also split architecture is favorable for performance optimization and load management. Also, it facilitates network function virtualization and software-defined networks. So in this respect, option 1 through option 8 different functional splits are defined, and option 2, the interface between the CU and the DU is defined and standardized by 3GPP. So here on the CU would be the RRC and PDCP layers. on the DU would be everything from RLC to RF in one unit. Yeah. Then coming to the option 6, the small cell forum, the organization which is responsible for interoperability between small cells, and also they found the option 6 is suitable for small cells, and they are defining the interface for option 6 and also standardizing it. And likewise, option 7 promoted by Oran, and then option 8 is the primitive way where all the layers from Phi to RRC were in one unit, and then the RF and the interface between was a proprietary interface. So now let's look into the details of functional split option 6. So option 6 here, as you see, there are three different units. The SRU, the radio unit with the Phi and the RF layers. And then we have the SDU, the distributed unit on a separate hardware, which could be off-the-shelf server PC, and on that is the MAC and RLC layers. And then we have the centralized unit, SCU, and on that would be the RRC, PDCP, and SDAP protocols. The SDAP is a service data adaptation protocol, maintaining the quality of service. So here, as you see, it's an independent radio unit design, meaning to say the entire Phi and RF is in one unit. And the interface between the MAC and the physical layer, which is promoted and defined, maintained by SCF, the small cell forum, is called the 5G NFAPI, network FAPI. And this interface would facilitate when the DU and RU comes from different vendors. It also low requirements on the NFAPI in terms of delay and bandwidth. Going forward, so this is how an option 7 would look like. So here you can clearly see the high Phi and the low Phi split, and the interface between the high Phi and low Phi is the open fronthaul defined by Oran Alliance. Yeah? And also above you can see those functions which are part of the high Phi and the low Phi. It's a split Phi architecture, and stringent timing requirements, bandwidths, and synchronization requirements are on the open fronthaul, because the two parts of the physical layer have to operate in tandem in order to have those beams formed perfectly. Yeah. And then we have, as usual, the 3GPP F1 interface between the distributed unit and the centralized unit. Also, these kind of architectures, as you see, the CU, the DU, and the RU can come from different vendors. So that is where you have now a diversity in the supply chain. And secondly, due to the reduced functionalities on the radio unit now, the cost of the radio units are cheaper and in a direction of commoditizing the radio units to provide affordable networks, 5G networks across the globe. So with this, let's move on to the small cell architectures. So here you see the layers from physical to RRC and RF layer, and the possible different architectures. One is a small cell with, it's an all-in-one integrated small cell. It contains all the layers from RRC through Phi and RF in one unit, and within the all-in-one integrated unit, the small cell can still use the FAPI interface, the open interface, to communicate between the MAC and the Phi. And then next is about a 2-unit small cell. Here you can see the split, and the radio unit is on a separate hardware, and the CU and DU is on a separate hardware. It's called the 2-unit small cell. And coming to the last architecture, which is the 3-unit small cell, here you can see the dual split, one at the front hall and the other one at the mid hall. So the 2-unit small cells and the 3-unit small cells architecture helps in virtualization of the networks, in moving the DU and CU to a cloud and pooling them to provide efficient scheduling, also to control the radio units, multiple radio units. Further, if you look at the statistics, how are these architectures growing over time? So now the all-in-one integrated small cells are the majority and dominant, and this will remain for the next couple of years until 2023, when the split architectures, the dual, the 2-unit and the 3-unit small cells will grow in numbers, and by 2026 you will see a slight decline in the integrated small cells, and by then you can see the percentage of the different variants: 22% of integrated small cells, 26% of these 2-unit small cells, and the 32% of the 3-unit architecture, right? And the remaining is the distributed antenna system, the DAS. So next, coming to the 5G network evolution. So we have talked about the open and standardized interfaces, which leads to disaggregated RAN, and then network operators are embarking on a virtualization journey, and which means to pull the DUs, virtualize the DUs, and pull them into the cloud. Likewise, the centralized unit, CU, and the RAN intelligent controller, the RIC, onto the cloud for efficient resource management and efficiency, and also network automation and so on. One message here: the network can include disaggregated units, the all-in-one integrated units, and also together with the macros, but the network architectures should be flexible to meet the end requirements, meaning to say there is no one architecture which fulfills the different deployment scenarios as required by different use cases. So always we need to go by flexible network architectures and to meet the end customer requirements, which could be latency, capacity, quality of service, security, etc. And for Rohde & Schwarz, we focus on testing the radio units, which is the PHY and the RF layer, irrespective of it is an integrated small cell or a distributed unit. Let's move on to the next section, which is about the test and measurement. So we serve the entire small cell ecosystem. As you see, we offer solutions for R&D through production, be it a chipset company, module vendors, small cell makers, network operators, and test labs. Yeah. So let's have a look at the small cell diagram here. And as you can notice here, the baseband signal comes from the baseband unit, which hosts reference clock, digital interfaces, the memory, and also hosts functions like coding, modulation, etc. And these baseband signals are further processed in the RFFE, the RF front end, within the radio unit, and the antennas are now tightly integrated with the radio unit, the RFIC on the radio unit, and the communication to the UEs would be through beams now. Yeah. So now let's look into the challenges and solutions through the different subsystems, yeah, of a small cell. So let's look into the digital design first. Signal integrity and power integrity are the fundamentals of signal digital design. So here, due to the increasing integration densities, high-speed digital interfaces, it imposes lower jitter and noise limits for signals, and within the signal integrity you have many tests like interface test, the PCB and interconnect test, the clock tree, the PLL, ADC and DAX. And power integrity, here the challenge is to find suitable probes for measurement on the different power rails on the board. Power supply test and oscillator phase noise has an impact on system performance. Of course, all these tests, signal integrity, power supply test, phase noise measurements can be done with the R&S oscilloscope, the RTP and the RTO. So the oscilloscopes provide excellent insights on the time domain and also on the RF domain. And the oscilloscope covers all of these measurements for signal integrity and power integrity together with protocol level debugging on the interfaces. So then if you want a specialist for phase noise measurement, so then we have the FSWP, the phase noise analyzer. Together with this, we have the test bench essentials like the power supply, the NGP 800 going up to 800 watt, and the digital multimeter. Yeah. So next, moving on to the front-end design and testing. Here, there are many components like power amplifiers, filters, LNAs, mixers, etc. Let's choose the power amplifiers as an use case or an example. So here, if you take the power amplifiers, we need to measure the gain and the EVM performance, and we also have methods like DPD, the digital pre-distortion, which is used to enhance the linearity of the power amplifier operating in its nonlinear range. Specific challenges of DPD would be higher bandwidth of millimeter wave, the varying DPD models, and the memory-based DPD. So here, if DPD is properly implemented, it can result in an improved EIRP by up to 3 dB, which means you have reduced antenna elements in the millimeter wave array to hit the same EIRP target without DPD. So that's excellent news. So for proper implementation of DPD, you need to measure, and for that you have the setup with the SMW200A, the vector signal generator, top class, well accepted in the industry. And the R&S FSW, which is the signal and spectrum analyzer, again top class. These are like kind of a couple which is very well accepted in the industry, especially the infrastructure market. And here you can also see the LAN to control and also transfer the polynomials and the distorted waveforms to the generator. The next solution is the network analyzer. There you see the R&S ZNBT. It's a true multi-port network analyzer with 24 ports, and you can do testing on multiple devices. And of course, one of its special use case is to measure the mutual coupling between the antenna elements in an array. Without the multi-port network analyzer, when you use a single port to stimulate one antenna element and then measure the mutual coupling compared to stimulating all the antenna elements and then measuring the mutual coupling, this makes a lot of difference in the performance. So this is possible with ZNBT, and it can also be used for filter measurements and antenna measurements. Moving on next to the antenna measurements, here due to the tight or high integration of the antenna in package and the RFIC, we have to do these tests over the air, as we don't have access to a RF port to do the measurements. So testing in over the air means we need chambers, and here I would like to introduce the ATS 1000, and here you can see the ATS 1000 as multiple use. So one for antenna characterization, and then you can also do modulation performance tests like AVM and ACLR when used together with VSG and VSA. So the antenna characterization, here you need the VNA, Vector Network Analyzer, and our choice is the R&S ZNA. And for the EVM and ACLR, the modulation performance for active antenna system, this would be the SMW200A and the FSW. So with millimeter wave, it's important to test the components for thermal effects. And as you can see on the chart here, when you measure a power amplifier over different frequency, over a range of frequencies across different temperature range, you have different performance. This makes testing the components, especially in the millimeter wave range, across the different temperature ranges, because this could have an impact on the overall system performance if you don't do that. So for that, the ATS 1000 chamber can be equipped with a temperature testing option. The white color bubble, what you see there, we call it as the temperature bubble, and this temperature bubble is made of Roha cell material, which is transparent to RF radio frequency, which means your measurement values are not disturbed because of the temperature bubble inside the chamber. How do you control the temperature is by blowing hot air or cold air into this temperature bubble so that the absorbers are not destroyed, right? So this was one of the critical factors. And then moving on to the beamforming characterization of 5G new radio FR1 downlink signals, which is the transmitter characterization. So here you need phase coherent acquisition of base station output streams, and also do multi-channel demodulation and analysis. So for this, we have the R&S oscilloscope, the RTP model, and together with the RTP, you need a software called VSE, the Vector Signal Explorer. And as you can see, the base station 4 output streams are directly connected to the 4 channels of the oscilloscope. And the oscilloscope by default is phase coherent. So phase coherence is provided by design. And this signal is digitally down converted to IQ signals and provided to the VSE software, which is on an external PC. And this software does the measurement and analysis using the IQ data. This was solution for 4 channels. Now if you want to see solutions for more channels, so here we'll have to look at the NRQ6, the frequency selective power sensor. As you can see from the rear view there, we have Ethernet connection on this power sensor. And the function of RTP can be done by the NRQ. So when we serially connect these NRQs, we can do measurements on up to 8 output streams. So here in the diagram, you can see the output of the base station is connected to a switch matrix, an RF switch matrix, which sequentially switches between the different power sensors. And the power sensor Ethernet connection is connected to an Ethernet switch, and which is in turn connected to the VSE software, which is on an external PC. So this setup is used for testing on 8 channels. Here we have one master NRQ as master for reference, and then the remaining as slaves for measurement. So this setup can be extended up to 64 streams, to measure up to 64 streams. And the VSE software also does measure the phase difference measurements on all available demodulation reference signals. So this was about the transmitter beamforming characterization for 5G new radio FR1. And some customers we know, they also use this solution for measuring the the FR2 performance at IF frequencies. So with this, let's move on to the most important test, the conformance testing. So for conformance testing of small cells, we do follow the same specification as we do for the base stations, which is the 38.141-1 and -2 for the conducted testing and the radiated conformance testing, except for we have to now observe the limits according to the base station classes, low area base station and medium range base station. So here in example, I am using a millimeter wave use case, because just to share with you how the testing of a millimeter wave involves a different test methodology. So here we use for millimeter wave an anechoic chamber for testing with test antennas, and again when it comes to the instrumentation, it is the SMW FSW. When it comes to the test coverage, we cover all the test cases from 38.141-1 and -2, chapter 6, 7 and 8, which corresponds to the transmitter, receiver and performance testing. With this, let's move on to the challenging part within the conformance testing. Here we have under chapter 8 the small cell performance test setup. So if you look at the measurement setup recommended by the 3GPP, on the left you can see it involves a base station tester, 4 channel simulators, 2 AWGN generators, and then a base station under test, and the inputs are given to the receivers of the base stations. And from the base station under test, there is a hark feedback back to the base station tester. So here, this whole setup can be simulated using the SMW200A, which is a dual channel instrument with inbuilt fading and AWGN. And this complete setup can be simulated with one box. The outputs of the SMW200A is directly connected to the receiver of the small cell in case of an integrated small one unit small cell. In case of disaggregated units, so the radio part, the physical layer and radio part is within the SRU, and the SRU would replace the small cell. It is the same setup, and then here you can see the radio unit would provide the hark feedback based on which the SMW200 will decide to transmit a new block, transport block, or to repeat the previous transport block. So one box for such a complex scenario means reducing the cost of test. So as we learned for millimeter wave small cells, we need the chambers to do the measurements. So here I show a part of the Rohde-Schwarz portfolio, chamber portfolio, which are suitable for small cells. So here, starting from ATS 1000, which I introduced already in case of antenna in package measurements. So this covers frequency range from 18 to 87, and this is a direct far field measurement, and the quiet zone would be around 5 centimeter at 30 gigahertz, and the DUT weight it can take is about 20 kgs, and shielding effectiveness more than 50 dB. So this was used for direct far field measurements. So coming to the ATS 800R, so this is a cost-efficient shielding chamber. As you see, this is a test track changed to a chamber, shielded chamber, and you do have space for instrumentation, and especially you have to look at the Qatar reflector used in both ATS 800R and ATS 1800C, which means this is a indirect far field measurement. So thereby you have a bigger quiet zone now. So with 800R you can have up to 20 centimeter quiet zone, 1800C you can have up to 30 centimeter quiet zone, and the 1800C can now take 15 kgs of DUT weight, much suitable for all kinds of small cells, and then it also offers the highest shielding effectiveness of more than 90 dB. So coming to the last chamber, which is the R&S CMQ200, mainly meant for production. The original form factor of this chamber is until the blue marker which you see there. The length of this chamber can be extended with an option so as to test devices like small cells. So the frequency range here of the CMQ200 goes from 20 to 77 gigahertz, suitable for FR2 measurements. Like the CMQ200, we have another box called CMQ500, which has the same form factor of the CMQ200 but covers wider frequency range, covers both FR1 and FR2, goes from 0.7 gigahertz to 77 gigahertz, and also has higher shielding effectiveness of 80 dB, while the CMQ200 has about 60 dB shielding effectiveness. So coming last to the production test. So here I list the different RF stages in a production line where they use RF instruments, and one of them is calibration. The calibration algorithms are quite unique to the manufacturer, and then next, coming to the verification, often it is a subset of 38.141 test suite, but the test case selection is largely and strictly dependent on the manufacturer's test strategy. And also the debug stations for repair and debugging the small cells and measuring voltages and currents at different test points, for which you can use an oscilloscope or a digital multimeter as introduced in the first during the digital design tests, right? And then coming to the solutions for calibration and verification in a production line, we do have two setups here. So one for FR1, which includes the signal generator SMCV 100B, and then the signal and spectrum analyzer FSB 3000 series. So this is a two-box solution, and likewise we have the SMM 100A together with FSB 3000 series spectrum analyzer for the FR2, and this is a two-box solution. As I said, many of these tests on the production line depends on the manufacturer's test strategy. Is existing ATEs or the ATEs which he is going to build, right? And some manufacturers prefer a two-box solution, that is the vector signal generator and the vector signal analyzer as two independent boxes. And then also some of the manufacturers prefers a one-box tester. To introduce more on the one-box tester, I would now invite Nico to give an overview of the one-box testers from Rohde & Schwarz.
Thank you, Mahesh. First, what do we mean with the term one-box tester? It means that we have a signal analyzer and generator built in one box, providing an attractive, slim solution for production. For the demonstration, I have brought the one-box tester CMP200 together with the remote radio heads, and we will operate in a loopback mode. The CMP200 has an RF interface, and combined with our remote radio head, it can generate or analyze millimeter wave signals. The analyzer and generator is capable of measuring within the 28, 39 and 47 GHz bands. This instrument has a total bandwidth of 1 GHz and comes with 3 ports. These 3 ports are very handy when it comes to parallel testing in production. The generator and analyzer can also be used as a normal one. So with the generator, it can replay continuous waveform signals, it can replay predefined waveforms or chipset-specific waveforms. The analyzer can perform IQ versus slot measurements, it can act as an IQ recorder, it can make power measurements and also analyze the spectrum. This instrument can perform the important downlink measurements which are necessary for the 3GPP new radio base station testing specification TS 38.141-2. The CMP200 came from a very successful product family, which had great production features implemented. One of them is our smart channel technology, which enables parallel testing on our 3 ports, enabling a higher DUT throughput per tester. We have designed a completely new sequencer for production testing, which achieves not only ultra-fast measurement speed, but gives also the possibility of quick modifications, which is key in the production environment. This tool is called Wireless Manufacturing Test, or short WMT. Let's now continue with the demonstration. I have created a test plan in WMT for the 3GPP test case 1.1. We are testing band 261 with a bandwidth of 100 MHz for the low, mid and high frequencies of the channel. So we are gathering our measurements. We are testing for modulation, which determines the quality of the signal. We have an overall EVM of 1.59% and a frequency error of minus 2.09 Hz. We are also measuring for the spectrum, so we are performing an adjacent channel leakage power ratio, or short ACLR, and also an operating band unwanted emission. For the spectrum measurements, we are measuring in the negative and in the positive direction of the carrier, and we can also apply some verdicts which we passed. For the mask, we have here different parameters which indicates the different thresholds of the mask. In addition, I can proudly announce that our cooperation with Qualcomm was fruitful. The CMP200 is fully validated within QDOT for calibration and verification of their small cell chipset since the July 2021 QDOT release. On the right-hand side of the slide, you can see all the different test cases. The CMP200 is fully validated. Mahesh, I think we have shown a lot of different solutions. Could you please summarize it for us?
Sure, Nico. So far, we have presented a wide portfolio of solutions for small cells ranging from digital design through conformance testing and production. Most of the solutions we presented today also support multiple technologies like LTE and Wi-Fi coming from the cellular and non-cellular domains. The challenges with 5G small cell testing is we need highly reliable, flexible end-to-end solutions. As a long-term partner for the communication industry, Rohde & Schwarz offers a comprehensive portfolio for small cell testing for today and tomorrow. With this, I would like to conclude with some summary points that small cell plays an important role in realizing the full potential of 5G. Future small cells are ready to support open and standardized interfaces, thereby facilitating disaggregated RAN architecture, and Rohde & Schwarz providing the wide portfolio. We are the one-stop for all your testing needs. With this, I come to the end of the slides which I had prepared for you for this presentation. On behalf of the team, I would like to thank you for your attention and appreciate your time. Thank you.